Welcome to our introduction on eigenvector and eigenvalues in data science. You might be wondering, what are these unique terms? Let's break them down. Picture a square. Imagine pushing or pulling its corners. It might stretch into a rectangle or flatten into a line, but regardless of how you change it, there are specific directions where the shape changes the most. These directions are what we call eigenvectors. When we deal with a matrix, the eigenvectors guide us in understanding the direction of any changes or transformations. They have the power to reveal hidden or underlying factors in our data, which we often refer to as latent dimensions. Take, for example, a scenario where customers are rating movies. If we examine the eigenvectors in this situation, we might unearth the importance of the movie's genre. In simpler words, the eigenvector can assist us in understanding the extent to which the genre affects a customer's rating. It acts like a detective tool, helping us discover hidden patterns within the data. Now, you might ask, how much does the shape change along these directions? That's where eigenvalues come in. They're the numbers that tell us the exact amount of change along these special directions. In the context of data science and statistics, eigenvalues do indeed help explain the variance in the data. In data science, eigenvalues and eigenvectors help us simplify complex data. They show us where the data varies the most and by how much. This is incredibly helpful when we're dealing with data with many variables. To compute eigenvalues and eigenvectors, we use a Python library called Numpy. It makes these calculations simpler and faster, allowing us to focus more on understanding our data and less on the intricate calculations. As we proceed, we'll delve into this in more detail. So, let's get started. To leverage the ideas presented in the first slide, let's further expand on the role of eigenvectors and eigenvalues tours in data analysis. Eigenvectors serve as representations of hidden dimensions or latent values within the data. They provide valuable insights into the underlying structure and relationships among variables. However, interpreting eigenvectors often requires domain knowledge and expertise specific to the context at hand. Eigenvalues, on the other hand, quantify the magnitude of these hidden dimensions. They indicate the degree of influence or stretch that each dimension has on the variability of the data. By examining eigenvectors and eigenvalues, we can uncover essential information within different data analysis scenarios. For example, when analyzing viewer ratings of movies, eigenvectors can reveal latent dimensions such as genre, shedding light on the significant impact certain genres may have on viewers' ratings. Similarly, in text analysis, eigenvectors can uncover latent topics within a collection of documents, aiding in understanding the prevalent themes. In the field of healthcare, exploring eigenvectors derived from patient symptoms can help us discover hidden diseases and understand the underlying relationships. Overall, leveraging eigenvectors and eigenvalues empowers us to gain profound insights and make informed decisions across diverse data analysis scenarios. They serve as powerful tools for uncovering and understanding the underlying structures and patterns hidden within our data. The role of eigenvalues and eigenvector in data analysis. They play a critical role in data analysis. Consider a matrix filled with movie ratings by different customers, like this. In this matrix, each row corresponds to a user, each column corresponds to a movie, and each cell contains the rating given by that user to that movie. By analyzing the eigenvectors and eigenvalues of this matrix, we can uncover hidden dimensions of the data. For example, we might discover that the eigenvectors indicate a strong influence of movie genre on ratings. The corresponding eigenvalues would then tell us how strong this influence is. In the next slides, we'll delve deeper into how to calculate and interpret these values using Numpy, a Python library. Welcome back to the movie ratings analysis. In this matrix, we have ratings given by 5 viewers for a selection of. In this example, we can observe that among these viewers, we can clearly identify 2 distinct types of movie lovers. The first group consists of individuals who are avid fans of hero movies, marked in red, while the second group shows a strong preference for sci-fi films, marked in blue. Let's explore this intriguing pattern in the following matrix, where each cell represents a viewer's rating for a specific movie. Keep an eye out for the contrasting ratings between hero and sci-fi movies, as it sheds light on the diverse tastes and preferences among these movie enthusiasts. Next, in this code snippet, we are analyzing a matrix of movie ratings. The matrix represents ratings given by 5 viewers for 5 different movies. Specifically, we have 3 hero movies and 2 sci-fi movies. We begin by importing the necessary libraries and initializing the movie ratings matrix using Numpy. Each value in the matrix corresponds to a viewer's rating for a particular movie on a scale from 1 to 5. Next, we perform an eigenvalue decomposition on the ratings matrix using the Numpy function np.l and lg.eig. This decomposition helps us understand the underlying patterns and preferences in the movie ratings data. We then print the eigenvalue, which represent the magnitude or strength of the corresponding eigenvectors. The eigenvalue provide insights into the amount of variability captured by each eigenvector. Finally, we print the eigenvector themselves, which represent the directions or patterns in the data. Each eigenvector corresponds to a particular aspect of the movie ratings. By examining the printed output, we can observe a clear distinction between viewers who prefer hero movies and those who prefer sci-fi movies. This distinction is evident from the patterns and weights associated with the eigenvector, where some viewers consistently rate hero movies highly and sci-fi movies lower, while others exhibit the opposite preference. More on the next slide. In our analysis, we will focus on the first two eigenvalue, which have the largest values capture the most significant patterns in the data. Then we can disregard the rest of the data, as these eigenvalue encapsulate the majority of the variation within the data. By now we know that there are two latent dimensions in the data. Now it is up to us to offer an interpretation to these values. Now we can look at the eigenvectors. The first eigenvector has fairly consistent values, all ranging around 0.4. This reveals a consistent trend. Viewers consistently rate hero movies higher and sci-fi movies lower. This suggests that some users will consistently rate certain movies higher and give lower rating to genre that they dislike. These numbers might indicate consistency in rating for certain users. Now, let's shift our attention to the second eigenvector. It unravels an intriguing distinction between the genres. Negative values associated with hero movies and positive values linked to sci-fi movies indicate a clear divide in viewer preferences. These values might indicate a rating going to opposite directions. This could be interpreted as follows: some viewers lean towards the heroic narratives, while others gravitate towards the world of sci-fi, and this could be very distinct, someone liking only one genre but not the other. Finding a consistent interpretation from eigenvalues and eigenvector alone can be challenging. While these mathematical constructs provide valuable information about the variability and patterns in the data, their direct interpretation in the context of specific features or phenomena can be complex. Eigenvalues and eigenvector capture the underlying structure and trends in the data, but they don't always have a direct and intuitive correspondence to the original features or factors. They provide a new basis for representing the data, often in terms of orthogonal directions of variation.